Welcome. This is the Chemical Engineering First Year Night. Chemical Engineering, a brief introduction. I feel that I really have to do this. I think there's a lot of people here who really don't know what chemical engineering is or think about in a slightly different way. I'm Tony Young, the Associate Chair of the Department of Chemical and Materials Engineering. Feel free to contact me if you have any questions or, that you want to follow up. Before I start, I should also acknowledge that we're located on Treaty 6 territory, and we respect the histories, languages, and cultures of First Nations, Métis, Inuit, and all the First Peoples of Canada, whose presence continue to enrich our vibrant community. So let me begin. What is chemical engineering? I mean, that's a question all of you have in mind, right? Now, if I could be a little bit of a wise guy, you either know what chemical engineering is, or you don't know what chemical engineering is. Well, that pretty well covers everything, right? You either know it or you don't know it. But actually, there's a third possibility, and that is you may have the wrong impression of what chemical engineering is. And if you do, hopefully I can clarify some of this stuff. And I would stick my neck out a bit and venture to say that more than half the people here probably belong to the second or third category. You know, you either don't know it or you have some misconception about chemical engineering. So what is it? Well, let me start with what does a chemical engineering do? Just like any other engineer, we make things. We make things out of something. In our case, what we usually do is we make value-added products out of raw materials. Well, how does that distinguish us from other types of engineering? When you make value-added products out of raw materials, a lot of times you have to change the identity of the molecules that you're working with. One example would be if you take methane, CH4, and combine it with water vapor, and you produce hydrogen and some other gases. That is chemistry, right? That is changing the identity of molecules from this to that. And in that regard, that involves chemistry. That's really where our name comes from, chemical engineering, because it involves chemistry. Let me be very clear. We are not chemists. Chemical engineers are not chemists. Because what we do is we take the discovery in chemistry labs. Okay? Chemists do the discovery in their labs on the bench, you know, maybe even a small pilot scale things. But once they discover the science behind it, then someone else will say, that's really good stuff you just made, right? But instead of a beaker of it, can you make like a ton of it, tons and tons of it? Okay, so you want to scale up. That's where we come in. Chemical engineers come in. We take what is already discovered by chemists, and we scale them up. But scaling up is not easy at all. That is not something that a chemist is trained to do. They would not even want to attempt it. So we want to do this scale up on it's a large scale. We also want to do it efficiently, okay? Because after all, there's a bottom line, making profit. But the most important thing is we have to do it safely. Because when we scale things up, when we scale up a chemical reaction, you can imagine there's a lot of energy involved. There's a lot of could be high temperature, high pressure. Safety is number one priority as for any engineer. And when I say safe, it's not just the safety for the people who are in the chemical plant or whatever. Of course, they have to be safe. You have to also worry about the safety of all the neighbors. If you have a chemical plant, what about the people who live around there? Okay? So safety, not just to the workers, but also to the surroundings. And then now, more and more, we're realizing we actually are in control of a lot of energy. Like when you drive a car, you're actually controlling a machine that weighs 1,000 pounds or more, right? So you have a lot of responsibility to drive safely. But we have even more responsibility because we're handling so much energy that we have a responsibility to keep not just the neighborhood safe, but even the environment safe. The planet has to remain safe. Those are really big responsibilities. But if you combine all of these, that is what we call chemical engineering. So here's a cartoon that is meant to be funny, but it actually tells the story. So what you have here is a chemist, a guy, white lab coat, thick glasses, pocket protect. They do their chemistry job, and if the boss tells them you've made some really good stuff, scale it up, what do? Just make your beakers bigger, make your test tubes bigger. Is that how you scale up? No, that is not how things scale up. Like I said, a chemist would not try to do. There's a process behind it. I hate it when people say that. No, when people ask you to explain things, oh, and they say there's a process behind it. That's just kind of like, usually involves bureaucracy and all of that. But in this context, process means what is the process you need to take that chemical reaction and make it big, make it go, like I said, make it go efficiently on a large scale and safely. That is the process. In fact, I almost feel that the name chemical engineering is almost a misnomer. It gives people the wrong impression. Hopefully I can clarify this by the end of today. A better name for chemical engineers are process engineers, because we design processes to make things go on a big scale. We kind of call ourselves interchangeably as chemical engineers or process engineers. If I had it my way, I'll probably change the name of the department and call it process engineering rather than chemical engineering. What is the process? It's a typical flow diagram of an ammonia plant. Never mind all the details. All I want to show you is things are very, very complicated when you design processes. Of course, there's chemistry in there, but you also have to worry about how things flow from A to B, meaning you have to understand fluid mechanics. You have to know how heat goes from A to B, so that means you have to know heat transfer, and a lot of things. You have to understand thermodynamics. In fact, chemistry is probably the least thing you have to worry about, because it's already been worked out. What you have to know for your job to design processes, more like math and physics, not so much chemistry. So to properly design a process, because we're process engineers, you must be familiar with areas of fundamental science, many areas of fundamental science and engineering. For example, I'll just list a few here. For every bullet point, I can go like for an hour or more about what they mean. But thermodynamics, fluid mechanics, reaction kinetics, physical chemistry, a lot of things. The second last point, process control. Remember I said we have to make the process go in an efficient manner. Long time ago, I mean, right from the day one with the advent of computers, we realized, chemical engineers realized that machines react a lot faster than humans. They can make calculations a lot faster than humans. So right from the time when computers were still run by vacuum tubes, we had been using computers to control our processes. It's like your car, right? Next time you hop into a car and drive, what are the things that you do by hand, but do manually? You probably have a steering wheel, you control the signal when you turn, you step on the gas. Everything else is actually controlled by computers, microchips. So that's the same thing here. We have started using computers to control our processes right from day one. And with the latest thing of artificial intelligence, machine learning, and all that stuff, you bet we're taking advantage of those things. We have a lot of experts in our department who are really into machine learning and artificial intelligence, all of that, all for the purpose of controlling processes. And of course, the last one is safety and risk management. It sounds almost like cheesy. It's like Spider-Man, right? I mean, with great power comes great responsibility. We don't have great powers, but we have the ability to screw up a lot of things, kill a lot of people. So we have great responsibilities. So safety and risk management is a big, big part of our program. You see all these bullet points here. We have to be good in all of them. So in a sense, we're kind of like jacks of all trade. But in this case, we have to master a lot of these things. Well, there's so much to learn when you have to say, well, isn't this a really difficult program? No, I mean, we'll guide you through them. It's possible to master all of these without working you guys to some kind of unreasonable workload. It can be done, okay? Chemical engineering program will train you to do all of these things. Now, misconceptions about chemical engineering. There are quite a few. Let me just try to bust some of these myths. One of them is you have to be a wizard in chemistry. Well, if you listen to the name, it's chemical engineering, so I must have to have a lot of chemistry background. Not really. When I joined this department as a professor, my chemistry basically was stuck at first year chemistry. I don't know a lot of chemistry. If you are okay with chemistry, if you like math and physics, chemical engineering is for you. I can give you another kind of case in point. If you enter the chemical engineering program, how many more chemistry courses do you have to take? Do you know? One. Just one. And that is organic chemistry. And to me, organic chemistry is something that you have to take. Everybody should take anyway. I've heard people getting confused by the two words, hydrocarbon and carbohydrate. At least if you take organic chemistry, at least you know the difference between carbohydrates and hydrocarbon. So just one chemistry course. The rest is all fluid mechanics, heat transfer, thermodynamics, all of this stuff. And also process control, right? Computer process control. You use computers to control things, and that requires some knowledge of mathematics and so on. So you do not have to be a wizard in chemistry. You do not have to work in a chemical plant when you graduate. I came from the industry. I actually spent quite a bit of time wearing hard hats, steel-toe boots, and fire retardant coveralls, and that was a lot of fun. I really missed that time. So there's nothing wrong with getting your hands dirty in a chemical plant, but you don't have to. You have a lot of options. You have such a broad background in many aspects of fundamental science. You can be quite flexible in choosing your career path. So you don't have to wear coveralls and work in a chemical plant. You can be working in an office in a design company, and God forbid, when you get promoted, you may actually end up in management and so on. You do not have to work in a chemical plant. If you don't like that kind of noise and stuff, there are other career paths available as well. Now, this is a big one, oil and gas. A lot of people associate us with oil and gas. We are not oil and gas, okay? We're chemical engineering. Well, of course, we can do oil and gas. We can also do many other things. Oil and gas does not, N-O-T, not define us. And I'll show you some of the new programs we have later on. I emphasize this point. A strong background in chemical engineering opens the door to many career paths. When you were in high school, you heard your science teacher say, you take this physics, chemistry, and biology courses, right? And then you also heard the claim that chemistry is the central science. Chemistry is what connects, on one side, physics, on the other side, biology is central. It's central to many branches of science. And in that regard, I would also argue that chemical engineering is the central engineering, because we are actually a very eclectic kind of program that you touch on so many fundamental aspects of engineering that you actually have many options. So a background in chemical engineering opens the doors to many career paths, not just steel-toe boots and hard hats and working in a chemical plant. But there's nothing wrong with that. So the current focus of our chemical engineering program, both in teaching and research, if you come in, you can sign up for regular chemical engineering. We have 3 other options starting this coming fall, which is available to you guys. There's also a clean energy and sustainable chemical processes. There's a bioprocessing and biomanufacturing option. And then there's the last one is what I was talking about, computer process control, where you actually use computers, modern data science, machine learning to control processes, all toward the same goal, scaling things up safely, efficiently on the large scale. Starting fall of this year, which applies to you guys, it didn't apply to people even from last year, is that if you come into chemical engineering, there are actually 4 things you can do. One is just regular chemical engineering. The other one is regular chemical engineering, CPC. CPC is an acronym for computer process control. There's also chemical engineering clean energy option. There's also the bioprocessing option. Don't get the wrong impression. The first option, chemical engineering, doesn't mean you're learning less than the other 3. CPC, clean energy, bioprocessing, these are just added flavors to chemical engineering. Every one of these 4 pathways is based on hardcore chemical engineering. Think of it as this. Let's say you go to a steakhouse and you love a big piece of juicy steak. That would be your main course. Our main course here is chemical engineering. So whether you do regular chemical engineering, CPC, clean energy, these other things are just sort of side dishes. Everyone shares the same main course, same big piece of juicy steak. Chemical engineering may be a standard French onion soup or salad or something, but it's delicious. Okay, it's just as good as any other 3. The CPC guys may want mashed potatoes or something. You know what I mean, right? So these things are all, at the end of the day, you're all hardcore chemical engineers. If you're a vegan or a vegetarian, you don't have steak, maybe you have a big piece of tofu or something. If you think tofu is bland and tasteless, it's because you don't know what to do with it. What I'm saying, chemical engineering is the main course. For CPC, Clean Energy and Bioprocessing, there are these specific electives they have to take to bring them closer maybe to clean energy or to computer process control and so on. But everybody takes a large number of common core courses, like fluid mechanics, heat transfer, mathematics, different 3 mathematics courses. Everyone takes that. Okay, so these things, CPC and these other things, this is side dishes. Same main course. So are there jobs out there? If I put this up, of course the answer is yes, right? I just want to show you how many companies are hiring us. I just want to show the large number of options there is. Closer to our backyard, there's some newspaper clippings. Air Products is coming to our backyard in Edmonton. They're a major company in producing hydrogen. They even think that Edmonton, or in this vicinity, would be the kind of a center for hydrogen production, of transitioning to a hydrogen economy and so on. And then there's biomanufacturing. Even the oil and gas people are dumping in huge amounts of investment to do things in a more clean manner. So there are lots and lots of chemical engineering jobs out there. We have our YouTube channels about our chemical and materials engineering department, so you can check it out. So if you have any questions, just contact us anytime. Thank you. Our next speaker is Bryce Nelson. He was a recent graduate from our chemical engineering program. Bryce obtained his BSc in chemical engineering from U of A in 2020 and is currently pursuing an MD PhD double degree at U of A. He is interdisciplinary, so it kind of supports my point that in chemical engineering, you'll be very strong in a lot of fundamental aspects of science, engineering science and engineering design. And so his interdisciplinary advantage took him to study oncology in the Faculty of Medicine. He was involved in developing automating nuclear synthesis and chemical purification processes for radioactive isotopes, and the subsequent application precisely diagnose and treat aggressive cancers. Bryce has co-authored 10 scientific papers and has a book chapter under his name also. The processes that Bryce developed are used for weekly production of medical isotopes, which are exported from Edmonton to supply preclinical research and clinical trials for patients with advanced cancer across 6 countries. Outside of his studies, Bryce enjoys playing tennis, running, and skiing. And he's also co-president of the U of A Bench to Bedside Students Association and the president of Tennis Edmonton.
I'm Bryce, and I'm happy to be here to share a bit about my background, starting in chemical engineering, and my current research, where we're working to engineer a radioactive bullet that seeks and destroys advanced cancers. So a bit about me, I got my degree from the U of A in 2020 in chemical engineering, and I'm currently in the 4th year of my PhD in oncology in the Woost and Anderson research groups here at the U of A. And I started working in the field of radiopharmacy as a chemie undergraduate in spring 2018, and I worked in the cyclotron facility on South Campus for the last 2 years of my degree. So as Tony mentioned, I enjoy skiing, long distance running, and tennis. And I thought I'd mention that I met my PhD co-supervisor during my summer job as an outdoor tennis coach in 2nd year. And I thought I'd mention that just to encourage everyone to network as much as they can, regardless of where they are, because you'd be surprised who you meet in the least expected places. So to begin, I thought we should start with the periodic table of elements. I'm sure all of you are at least somewhat familiar with this. However, I would argue that this is an incomplete portrait of the elements, and that rather, if you expand the table for each of the isotopes of the elements, you get this, the Karlsruhe chart of nuclides. Isotopes are different elements, but they vary by the number of neutrons. So an isotope, you have the same number of protons, but you can have different number of neutrons and have different isotopes of the same element. So these squares in the middle here, these black squares are these stable isotopes, and these consist everything around us. However, all the other squares in other colors are unstable isotopes, and those are radioactive, so they decay, giving off emissions back to stable elements. When these undergo radioactive decay, they can emit gamma rays for diagnostic imaging, or they can also emit particles that you can harness for therapy. If you take one of these isotopes, these radionuclides, you can tag it to a targeting vector, and this makes a radiopharmaceutical. So radiopharmaceutical is essentially a radioactive drug. So you take your radionuclide, you can tag it onto the molecule in a stable form, and then you have your radiopharmaceutical for diagnostic imaging and or therapy of disease. So this biological targeting vector component can bring this radionuclide directly to diseased tissue for imaging or therapy. And an example of why this is so beneficial is you can see in this image here, this CT scan of a patient who does have a cancerous tumor. However, you can't really tell where the tumor is. This is just external X-rays passing through the patient. However, once you inject the radiopharmaceutical, which is specific for these surface markers on these diseased cells, then the tumor lights up in this PET scan, and the clinician can identify where the tumor is and what type of tumor it is. So how do we visualize the tumors? So we have two modalities, SPECT imaging. So this is where we have a camera that rotates around the patient, and the radiopharmaceuticals give off a single gamma ray. Or we have a more modern modality, PET imaging, where two collinear gamma rays are emitted 180 degrees apart, which allows a more precise triangulation and quantification. So in practice, how do we visualize tumors? This is a PET scan of a patient who has metastatic prostate cancer. So this means that the cancer has spread around his body, in particular to the bones from the initial site. And you can see all of the lesions in black here. However, after therapy, a follow-up PET scan was performed, and the cancer was nearly cleared from the body. And the only uptake that you see in black here are the kidneys and the bladder, which is the primary excretion pathway. So how did we achieve that therapeutic response? Well, it's using an alpha particle emitting radionuclide. So the PET scans that we used gallium-68 for diagnostic imaging, and to achieve the therapeutic effect, we simply swap out the gallium with the actinium-225, which can then precisely annihilate the tumors. If you look at the whole treatment cycle, we initially took a gallium-68 scan with gallium-68 PSMA to show the initial stage of the patient. And then after seeing that there was good biodistribution of the drug, the actinium-225 is then swapped in. And after only several cycles, this nearly completely cleared the disease. You can see there's hardly any lesions left, and PSA, which is a marker of prostate cancer, has significantly decreased. And you can also take follow-up scans with the gallium-68 radiopharmaceutical to track the treatment. So this is the true power of radiopharmaceutical applications for diagnosis and therapy. You can both see and treat a disease using the same molecular targeting vector drug. And most therapeutic modalities cannot do this. So how do we make radionuclides? Well, in Edmonton, we make them in the Medical Isotope and Cyclotron facility, which is located on the U of A South Campus. And this houses a 24 mega electron volt proton cyclotron, which is the jewel of the facility. It also has clean rooms for manufacturing sterile radiopharmaceuticals, as you can see here, with the capacity to supply Alberta's radiopharmaceutical needs. So briefly, how does a cyclotron work? Well, we bombard a target with protons to induce nuclear reactions that transmute the target, creating synthetic isotopes that don't exist in nature. And our TR24 cyclotron accelerates protons to 24 mega electron volts, and this means the protons are traveling at nearly a quarter the speed of light, and this is necessary to overcome the strong nuclear force holding the nucleus together so that we can induce the nuclear reactions. So how do we accelerate those protons? Well, we use alternating electric fields and we constrain the particles with magnetic fields. And this allows us, with the magnetic fields, to shoot the high energy proton beam out into a target. And what happens in that target material? So we have our high energy proton from the cyclotron. It slams into the nucleus and it enters the nucleus and kicks out either, say, a neutron or two neutrons. And this is what most cyclotrons can achieve because they're lower energy. But if you have a sufficient energy, you could also kick out three neutrons, a proton, two protons, a deuteron, or an alpha particle. And this is what our cyclotron at the U of A South Campus can do. So it lets us make many more exotic radionuclides that other cyclotron facilities cannot produce. And in general, why are we interested in cyclotrons to make radionuclides? Well, it's an alternative, safer way to meet increased demand for radiopharmaceuticals relative to using nuclear reactors, and we can produce isotopes that reactors can't. So this augments an aging, fragile supply chain of nuclear reactors. And importantly, there's no risk of a nuclear meltdown. So from a safety perspective, this is very appealing since once we shut off the power to the cyclotron, the nuclear reactions stop. I'll now guide you through one of the isotopes that we've made at the cyclotron facility, which is gallium-68 for diagnostic imaging. So first we have to make a target on the cyclotron. We then have to optimize our radiation. Then we purify the isotope out that we want from a radioactive soup that is left over after bombardment. And then we take that purified isotope and label it onto our drug. So first, to develop the target, we use a small coin, which is about the size of a toonie, and we use isotopically enriched zinc-68 powder, which is put in the center of the coin. We anneal that in so that it stays on during the irradiation, and it undergoes a PN nuclear reaction. So proton enters the nucleus, neutron gets kicked out. And as you can see here, we have to optimize our proton beam energy because there are different reactions that can go on in the target material. So we want to optimize our gallium yields while reducing potential impurities. This then goes in the cyclotron assembly here on the end of our beam line for irradiation. After we irradiate, we have lots of gallium-68. However, we also have other impurities that we don't want in our final product. So we use an automated synthesis unit to run an automated process which uses ion exchange resins, ultra-pure chemicals, and sterile filters to produce a purified gallium product ready for radiolabeling. And you'll notice here this automated synthesis unit is inside of a lead-shielded compartment which protects the operators from radioactive dose. Product purity and sterility is the primary consideration of this process. However, we also need to optimize for time because gallium-68 coincidentally has a 68-minute half-life. We're in a race against the clock to extract as much gallium-68 as possible from the process without sacrificing our purity. So we have radiation detectors throughout the automated synthesis box to track radioactivity through the process during time. And this way we can balance our radioactivity recovery with the time and achieve a good yield. So after we purify our gallium-68, we can do some radiochemistry to label it to our prostate cancer targeting drug. We can then inject it in a preclinical mouse model and image the tumors within the mice on a preclinical PET scanner. And this is a result. So you can see on the left, this image was produced using generator gallium-68, which is the traditional method of acquiring gallium-68. You can see the tumor here, kidneys and bladder. And then we went and took our cyclotron-produced gallium-68 and performed PET imaging, and we saw a very similar image. So this bodes well for cyclotron gallium-68 relative to the established generator gallium-68. So a more recent isotope that we've investigated is making lead-203 for imaging alongside lead-212 alpha therapy. So you can see here, this patient had metastatic neuroendocrine tumors around the body. And I'd like to highlight, again, these patients, they failed all other conventional treatments. So this really is, in some cases, their last chance. And after lead-212, DOTA-M-TATE, therapy, it nearly completely removed the tumor burden from the patient. What we can do is swap out, similar to the gallium and actinium, we can swap out lead-212, which is your precision nuclear strike on the tumor, with lead-203 to provide the diagnostic imaging. So ideally, we would want to pair lead-212 with lead-203 to do the diagnostic imaging because they're chemically identical. However, worldwide lead-203 supply is extremely limited. And why is that? Well, to make lead-203 on the cyclotron, you need to bombard thallium. And thallium is known as the poisoner's poison, so it's tasteless, odorless, water-soluble, and it's rapidly absorbed through skin and membranes. And it's a potassium mimetic, so exposure can lead to severe disorders and death. With this in mind, we need to design a safe and robust process. We modified our target, so we have our thallium pellet in the middle here. We have an aluminum disc, and we use indium, which can form a cold weld between a cover and the back of the disc to securely encapsulate the thallium metal. And we bombarded it on our cyclotron. We had to optimize our beam tune because we initially melted the target, so the heat transfer wasn't very good. But after we defocused the beam, we achieved much higher lead-203 yields. We then take our thallium target, we open it up, and we put it through an automated chemical process. And the end result is that we have highly pure lead-203. This is a gamma spectrum showing the different gamma ray emissions. And the only impurity of concern, lead-201, is hardly present at all. So in summary, for this, we modified our target. We designed another automated purification process. We also tested radio labeling, and we're now working towards lead-203 and lead-212 applications. And I'd like to highlight that this is not just preclinical research, it's also being used for clinical work. So it's bench and bedside. So for the past few years, we've been routinely producing and shipping our lead to customers at 13 sites across 6 countries for preclinical research and clinical trials. And we've patented this target technology, and it's being licensed to produce lead-203 in other countries. So I think it's fair to say it's a made in Alberta solution with implications worldwide. We've also adapted the target technology to make other attractive isotopes for PET imaging, including lanthanum-133 and 135, which can image actinium-225, as you saw earlier, and also copper-64, where there's limited supply but high demand. So in conclusion, radiopharmaceuticals have significant potential for diagnostic imaging and therapy of treatment-resistant cancers and many other diseases, such as viruses. This represents a paradigm shift in patient care, so moving from a one-size-fits-all approach like chemotherapy, which is like carpet bombing the body, to true precision medicine, where the treatment is tailored for the right patient at the right time. And Edmonton has the world-class facilities to supply isotopes for preclinical research and clinical trials in Canada and beyond. And I think it's fair to say that chemical engineering definitely gave me a good tool set to explore these diverse career opportunities in radiopharmacy and oncology. So I have some acknowledgements. I'd like to thank a number of people from the U of A and Alberta Health Services, as well as our commercial partners, Viewpoint, Molecular Targeting, and Perspective for funding our lead-203 development. To finish off, why chemical engineering? So I think chemical engineering, as Tony said, is an extremely diverse field with enriching employment and research opportunities. You are taught a lot of skills that allows you to work in many areas, and it certainly gave me a diverse tool set, allowing me to work in aspects of radiopharmaceutical production and create useful products that directly improve people's quality of life. If you have any questions after the fact, feel free to shoot me an email. Thank you.
We have a few speakers from CHESS, CHESS, which is Chemical Engineering Student Society.
Hi, everyone. My name is Sheila. I am a 5th-year chemical engineering trad student, and I am also one of the co-presidents of CHESS. I basically really wanted to share about my trad experiences with getting co-op jobs. I really want to share that your life does not end when you don't get into co-op. I've been able to get the opportunities to have a research job where I learned a bunch of different techniques in biology, which was really cool. But also currently I am working at Suncor's Firebag site, which is an hour out from Fort Mac. And it's really cool to get to actually be on site and like see how the process of oil gets extracted from the ground and processed and the plant gets made. A really good way to, get into looking for jobs is to get more experience with like clubs. And that is why I also joined chess. I feel like it's a really good opportunity to leverage the club experience on your resume for those work experiences and job interviews, especially because as a trad student, you won't get all the opportunities that co-op students have or the advantages that they have. So you need to really, I guess, work for it to get those job experiences. And for those who are going to go into chemical engineering, which I don't know why you wouldn't go into chemical engineering because we're the best discipline ever, our applications for assistant vice president roles will be rolling out in the fall. So make sure to look out for that when they roll out.
Hello, everyone. I'm Justina Rubias. I'm a fourth year chemical engineering CPC student, and I'm in co-op. I just wanted to talk about why you should kind of do chemi or like maybe consider it. So like Tony said, there's a lot of opportunities in the disciplines. I used to work at a pulp mill. That's actually me right there in a lime kiln. I was at a plant in Peace River. Now I work at ATCO, it's completely different discipline. It's so important to join clubs. I feel like with chemi, there's a lot of balance. I'm not going to bash other disciplines, but I heard a lot of my friends having a hard time balancing school. And I know first year I had a really hard time like balancing my life and classes. Like Math 101 was a killer for me. Probably for some of you too. I really enjoy the classes. Like fluid mechanics, thermodynamics were like my favorite classes, and I'm so glad I did chemi. The reason why I did chemi is because of my mom, and I don't regret it. Like Tony said, there's 4 program electives if you're just a normal chemi student. However, like other disciplines, they don't have that leeway. And with chemical engineering, if you're not really sure like what you want to specialize in, there's like a lot of different options you can take. So I took project management as one of my program electives. I know some of my friends, they're taking like fuel cells. You can take some science electives too. There's a lot of different things you can take. And if you have any questions, please ask me about co-op, chemical engineering at the end.
I am a 5th year and last year co-op CPC student. So for CPC student, it's stream. It's basically is like a regular chemical engineering stream, but 4 electives are chosen for you. 3 of them are CPC specific electives. I actually put a picture of my MATLAB code in there for one of my CPC classes. It was supposed to be Python, but I couldn't really find any pictures. So if you are interested in Python, for instance, you would have the opportunity to learn how to use Python, to code with Python.
Hi everyone, my name is Janelle Henderson and I'm in 4th year Chemi Trad. I'm a transfer student. I actually came back to school after completing a chemical engineering technologist diploma from SAIT, and then I worked for 2.5 years at Imperial Oil's Curls site, where I was a laboratory analyst. And you guys are probably wondering, well, if you worked in industry, why would you come back to school? At SAIT, they taught a lot of like the technical aspects of chemical engineering, and like they showed like the physical part, but when it came time to like understanding like how things actually worked, like the theory and the principles behind it, it wasn't really like, I wouldn't say like industry gave me some of that, but like I still had questions about things, so that's why I decided to come back to the university to get my degree. And like everyone else was saying before, there's a lot of opportunities. So when you do trad, yes, you don't get the co-op experience, but there's plenty of opportunities. So like Yosola was saying, I did a DRA with one of my professors where we were looking at polymer reaction engineering and actually studying the effects of what happens during grafting polymerization. That actually was the key identifier of why like I am going to go pursue grad school. Like that's when I decided I wanted to do grad school, because originally I wanted to go back to industry afterwards, but with all the opportunities given, so like you guys can see on the slide, I was with one of the students that got to go to the conference in Calgary for chemical engineering. You guys can also see my capstone as well, where we looked at depressurizing a natural gas compressor as well. Honestly, Opportunities are endless as well. So like you'd be surprised like what you guys say yes to. And other than that, like honestly, if you're given an opportunity, in my experience, I would say yes. Go ahead and do it. If you guys have any questions, you can also email like the Chemical Engineering Student Society email too.